Download this code from codegive.com, link in the description below. OK, let's dive into part 3 of our hidden Markov model, ice cream example. In this part, we'll focus on decoding, finding the most likely sequence of hidden states given a sequence of observations. We'll use the viterbi algorithm for this. Recap, the ice cream Let's briefly recap our ice cream example and the elements. Asterisk hidden states, states the weather. We have two states. Asterisk H, hot. Asterisk C, cold. Asterisk observations, emissions what you observe, which is the number of ice creams Alex eats each day. We have three observations. Asterisk 1, 1 ice cream. Asterisk 2, 2 ice creams. Asterisk 3, 3 ice creams. Asterisk transition probabilities. Asterisk the probability of transitioning from one hidden state to another. Let's assume these. Asterisk emission probabilities. Asterisk the probability of observing a particular emission, number of ice creams, given a hidden state. Let's assume these. Asterisk initial probabilities. Asterisk the probability of starting in each hidden state. Let's assume the viterbi algorithm. The viterbi algorithm is a dynamic programming approach to find the most probable sequence of hidden states for a given sequence of observations. Here's how it works. 1. Initialization asterisk. Asterisk create two matrices. Asterisk viterbi state, time stores the probability of the most probable path ending in state at time, given the observations up to that time. Asterisk backpointer state, time stores the previous state in the most probable path ending in state at time. We use this to trace back the optimal path at the end. Asterisk initialize the first column of the viterbi matrix based on the initial probabilities and emission probabilities for the first observation. 2. Recursion asterisk. Asterisk for each time step t, from 1 to the end of the observation sequence. Asterisk for each state s in the set of possible states. Asterisk calculate the probability of reaching state s at time t from each possible previous state s. Asterisk prob equals viterbi s, t1 asterisk p, ss, asterisk p, observation underscore ts. Asterisk choose the previous state s that maximizes this probability. Asterisk viterbi s, t equals max underscore s, viterbi s, t1 asterisk p, ss, asterisk p, observation underscore ts. Asterisk backpointer s, t equals argmax underscore s, viterbi s, t1 asterisk p, ss, asterisk p, observation underscore ts, store the maximizing previous state. 3. Termination asterisk. Asterisk find the state s at the final time step that has the highest probability in the viterbi matrix. This is the final state in the most probable sequence. Asterisk best underscore path underscore pointer equals argmax underscore s, viterbi s, t. Asterisk best underscore path underscore prob equals max underscore s, viterbi s, t. 4. Backtracking asterisk. Asterisk starting from the final state best underscore path underscore pointer, trace back through the backpointer matrix to reconstruct the most probable sequence of states. Python code example. Explanation of the code. 1. Initialization asterisk. V equals, creates a list V to store the viterbi matrix. Each element of V is a dictionary, where the keys are the states, H and C, and the values are the probabilities. The first element V0 corresponds to the first observation. Path equals, creates a dictionary path to store the back pointers. Path state will store the best path leading up to the state. The loop for state in states calculates the initial viterbi probabilities and initializes the path dictionary. It essentially says, if we're in state at time 0, what's the probability of that, given the initial probabilities and the first observation. 2 recursion asterisk. The outer loop for t in range, 1, len, obs, iterates through the remaining observations, starting from the second observation. The inner loop for state in states calculates the viterbi probabilities for each state at the current time t. Prob, previous underscore state, equals max, for previous underscore state in states. This is the core of the dynamic programming. It finds the best previous state, previous underscore state, to get to the current state, at the current time t. It calculates the probability of each possible path leading to state at t and selects the one with the highest probability. Vt1 previous underscore state, the viterbi probability of being in the previous state at the previous time. Trans underscore p previous underscore state, the transition probability from the previous state to the current state. Emit underscore p state obst, the emission probability of observing the current observation given the current state. Vt state equals prob, stores the maximum probability in the viterbi matrix. NuPath state equals path previous underscore state plus state, updates the NuPath dictionary to store the optimal path leading to the current state at the current time. We extend the previous optimal path with the current state. 3 termination asterisk. Prob, state, equals max, vlen, obs, 1 state, 4 state in states. After processing all the observations, this finds the state at the final time step that has the highest viterbi probability. This is the final state in the most probable sequence. 4 return result asterisk. The function returns the path state which represents the full path to the state that has the greatest probability. How to run the code. 1 save asterisk save the code as a Python file, example viterbi underscore icecream.py. 2 run asterisk open a terminal or command prompt, navigate to the directory where you saved the file, and run it using Python viterbi underscore icecream.py. Output. The output will be something like. This means that, given the sequence of ice cream observations 3, 1, 2, 3, the most likely sequence of weather conditions is hot, cold, hot, hot. The algorithm also outputs the probability of the sequence. Key concepts. Dynamic programming. The viterbi algorithm is a prime example of dynamic programming. It breaks down the problem into smaller sub-problems, solves them, and stores the solutions, in the viterbi and backpointer matrices, to avoid recomputation. Log probabilities. In real-world applications, you often work with log probabilities instead of probabilities directly. This is because multiplying many small probabilities together can lead to underflow issues. The result becomes too small to be represented accurately. Using logarithms, you can convert multiplications into additions, which are more numerically stable. Applications. Hums and the viterbi algorithm have many applications, including speech recognition, determining the most likely sequence of phonemes given an audio signal. Part of speech tagging, determining the grammatical tag, noun, verb, adjective, etc., for each word in a sentence. Bioinformatics, analyzing DNA sequences, protein structures, and gene expression data. Financial modeling, predicting stock prices or market trends. Next steps. Experiment, try changing the transition probabilities, emission probabilities, initial probabilities, and observation sequence to see how the results change. Asterisk log probabilities asterisk modify the code to use log probabilities to improve numerical stability. Asterisk real-world data asterisk find a real-world dataset that you can model with an HM and apply the viterbi algorithm to it. Asterisk hidden Markov model libraries, consider using libraries like HM-learn in Python, which provide pre-built HM classes and functions, which can make implementation easier. I hope this detailed explanation and code example have helped you understand the viterbi algorithm and how to use it to decode the most likely sequence of hidden states in an HM. Let me know if you have any other questions.